So last time we wrote the hydrogen atom problem, in particular the bound states of this three-dimensional potential, which I draw here. Okay. So we rescaled all variables. If you remember, we were able to just eliminate all the h bars, the mass, and things by working with appropriate lengths and appropriate energy. The length is essentially the effective Bohr radius, and the energy is the Hartree. Also, we simplified considerably the two-body problem until we reduced first to a one-body problem, the relative motion. And then, by exploiting the central nature of the potential, we also eliminated angular momentum from the problem, okay, in a sense that we assume that we know the following thing. We know to construct functions of the angles such that this is just a constant, okay? And also Lz, y, Lm. Okay, such functions of the angles are known as spherical harmonics, and it is known, and we will show next time, how to construct them as common eigenfunctions of L squared, the total angular momentum, and Lz. Okay? L is an integer, could be 0, 1, 2, whatever. Okay? And M, given L, goes from minus L up to plus L in steps of 1. So there are really two L plus 1 values of this integer, which are, however, not explicitly present in the Hamiltonian. We saw, in fact, that the problem for the states with now negative energies, okay, which we'll have to find, okay, we still don't know where they are and how many they are. What we know is that they have a negative energy because the potential reaches 0 at plus infinity, and from here on there are scattering states, so states in which the electron is not bound to the nucleus but really flies off to plus infinity. Okay, so the potential, the problem we have to solve looks in these rescaled variables as follows. Second derivative of a radial function or something that is related to the radial function. We discovered that the right variable to use is really r times the radial function. Okay? Generally speaking, we saw that this should depend on some label, which we don't know, and on L, the angular momentum quantum number L. Okay? So therefore, U also will depend on that. Okay? So this is coming from the Laplacian. Then there is a term that still comes from the Laplacian. And this object is the angular momentum square part of the Laplacian. Remember that the Laplacian admits a decomposition into a radial part and an angular part, and that is the angular part related term, okay? Where I use, obviously, the spherical harmonics. Then there is this term that is minus 1 over rho, which is exactly the Coulomb potential, minus 1 over r. By the way, rho is simply r divided by the effective Bohr radius, okay? So this good unit of length. Also, this object here, in principle, I should write it as U tilde. U tilde of rho is simply U evaluated at Bohr radius times rho. This is a length, okay? And there is a square root of the Bohr radius in front, just to make the normalization happy. By the way, the normalization of this thing, before I proceed, is that the integral of u tilde of rho modulo square should be equal to 1. Okay? So the equation, let me finish writing it, we wrote last time is the following. Okay? I wrote every symbol. In fact, I will soon get rid of most of these tildes, for instance, perhaps except for this. Okay, so this is the energy we are seeking to find divided by the R3. Okay, so it's the dimensionless energy. So if I find 1/2 or minus 1/2 means minus 1/2 R3. Okay, so this is the equation we have to solve with this normalization in principle. Now, how do one solve this thing? E is, by the way, a negative energy. Okay, so this thing is less than 0 because we want the bound state. If E was positive, we were looking for scattering solutions, so solutions where the wave eventually becomes like a plane wave, so extended. Okay, the procedure to solve this type of equation, not only this, but it's a kind of, is the following. We have to work out what happens to this function for small r first and for large R. I say R instead of rho, it's the same thing, okay? So let us first look what happens when rho goes to 0 and then when rho goes to infinity, to get an idea of how the function should behave on those things. Given these two limiting behavior, we will be able to make a clever ansatz on change of variables and things like this. Okay, this is quite a standard trick that you should learn to use in more general circumstances. For instance, for rho going to 0, a very natural idea is that the solution might be some power of rho. So you say u of rho. Let us suppose that it starts some constant times rho to some power alpha. That doesn't mean that the function is equal to this. It is this plus things that have smaller power. I mean, power that are less important. And here I should distinguish between two situations. For instance, if alpha is positive, then obviously a larger alpha means just smaller function. Okay, so you should take the smallest positive possible term in a power. When alpha becomes negative, obviously the function really diverges. Okay, but once again, the more negative, the more it diverges. So in some sense, the smallest exponent, be it positive or negative, is always the most important one. Okay. We'll make comments about negative exponents because actually it's physically not very plausible. In fact, you should discard situation where this function really diverges. But how do we, on what basis do we argue about this alpha? It's very simple. Let us see. Suppose I eliminate the tilde because it's too much writing. Let us start assuming this and take the appropriate derivative. So the first derivative of u would look like a times alpha rho alpha to the minus 1. You realize that you have decreased the exponent. It means, I mean, a stronger thing. For instance, if this was, I don't know, rho square, this would be rho, which is greater. Okay? If this was, I don't know, rho cube would be rho square, so something bigger. Then I take the second derivative, and once again I reduce the exponent, so I get alpha minus 1 rho to the alpha minus 2. Okay, so you see the second derivative is kind of more prone to be bigger. All right, now let us see what the lowest possible order term do in the various places of this equation. You see immediately that this object here has this term, okay? So let me write it here. So this would be minus 1/2 times alpha alpha minus 1 rho to the alpha minus 2, obviously plus, let me write it like this, plus dots, okay? Whatever was plus dots here, that would be here, and that would be here, okay? Higher powers of rho, all right? Good, so this comes from there. What about this? Well, this you see has a 1 over rho square, and this has a 1 over rho. So it takes this behavior of thing, and it transforms into L plus 1 divided by 2, and then you have A rho to the alpha minus 2. Is it clear? Plus the usual dots. What about this? Well, this has minus A is in front of everything, okay? And then I have rho to the alpha divided by rho, so minus 1, plus the usual dots, okay? And this is it for this term. And then all this should be equal to this unknown constant times A rho to the power alpha plus dots, okay? So let us see. The smallest power is this. And it appears here and here. All other terms are higher power. For instance, this is alpha minus 1. You might say, hey, who is going to erase this alpha minus 1? The dots. Okay? There are higher powers here which will accomplish the cancellation of this. Here there is rho to the alpha. Who is going to take care of him? Well, the dots, here, here, and here, okay? Because there will be higher power that will exactly equate the right-hand side, okay? But who can make these two guys happy together in the sense that they should just cancel? Well, there's nothing can help but the fact that L plus 1 divided by 2, this coefficient, should exactly be equal to A over 2 alpha minus 1. And you see that the constant A is actually not important, as the 2 is not important. So what you want is a precise value of alpha, such that alpha minus 1 is exactly equal to L plus 1. So not any power is possible. Only what? Let us solve. It's very simple to solve this. It's a quadratic equation for alpha. You immediately see that there is a solution L plus 1. You see? If you put here L plus 1 minus 1 is L, so you have the L plus 1 and the L. All right? But there is also another solution, alpha equal to minus L. If you put minus L, this is minus L minus 1. The two minus just cancel, and you get, again, L plus 1. Okay? Any quadratic equation should have two solutions, and these are the two solutions. Okay? Now, I will argue with you in a second that this is physically acceptable, while this is physically unacceptable, and mathematically, obviously, unacceptable. Why? Okay. Let us see. You remember that L, okay, is a kind of centrifugal potential, okay? If I had to draw this potential here for various L, when L is equal to 0, then I have exactly this plot, okay, minus 1 over rho. But when L is positive, I have something like this. And the greater is L, the more this barrier increases, okay? Therefore, I expect that the greater is L, the less is plausible that the particle will actually visit the region small rho. Remember, u is the wave function. When you take the square, it will give you a feeling of what is the probability density of finding the particle there, okay? So the more you increase L, the less you should have probability of finding the particle close to the origin. And this is right in that, along that line. On the contrary, the more you increase L, the more you make alpha negative, which means the more the function diverges, which means the more density you have there, okay? So this already looks very weird for that thing. The only possible thing is when L is equal to 0. So this is certainly very bad. You might say, but if L is equal to 0, then, okay, so then this is simply alpha equals 0, okay? So for L equals 0, this predicts alpha equals 0, and this alpha equals 1. You might say, well, maybe both are acceptable. No, this is still not good, even for L equals 0. Why? Simple. If alpha is equal to 0, it means what? That the function u goes to a constant, right? Alpha equals 0 means constant in our way of writing power law. So if u of rho goes to a constant rather than to 0, at least linearly, as predicted by this other solution, okay? This predicts for L equals 0 something that starts like rho, okay? So something that starts linearly. Now, let us look what this implies in terms of the radial function, okay? The radial function corresponding to this, you see, should have a 1 over r behavior, okay? Because when you multiply, constant time divided by r. Because when you multiply by r, you find the constant that you have here, okay? Is this clear? On the contrary, in this case, you have just a non-singular behavior. You have some r that goes to some constant, okay? You see the difference between, so here, in this case, r goes to a constant. In this case, r goes to a constant divided by r. Is this clear? I need a nodding of that. Is this clear? Okay. I read from here. Depending on how u goes to 0, how u goes when the r goes to 0, okay, if this goes to a constant, then r goes to a constant divided by r. So this is the case, u going to a constant. On the contrary, if this goes to 0 linearly, then r goes to a constant, okay? I'm simply reading from here. There is a different r in front. Now, this is, I'm going to argue with you, not possible. Why? If I have a radial function that goes like 1 over r for L equals 0, remember this is L equals 0. Now, the spherical harmonics are actually very, very trivial for L equals 0. It's, we'll prove, it's just a constant, okay? So this function would not depend at all on the angle, and it would depend on r like 1 over r. But now a function like that, okay, if you apply the Laplacian to it, you know that the Laplacian of 1 over r is something like the delta. So you see, this is a quite singular equation whose Laplacian is a delta. And how can you eliminate a delta when you take the Laplacian piece? There is no possibility of getting rid of it because the potential has no delta, okay? The potential is just a 1 over r, but 1 over r is not able to eliminate this delta, okay? So this delta would be there, and it would not obviously satisfy the Schrödinger equation, okay? So 1 over r for the radial function, not good. Eliminate, okay? Which means also that this should always be eliminated, okay? So the functions actually have to start from 0 at least as linearly, okay? Which also implies that u of 0 is always equal to 0, okay? It's a kind of boundary condition. You see, in this half line, the problem is just in 0 plus infinity, the function not only has to be integrable, the square of this function has to be integrable, but in the origin, it should go to 0. Okay? And it goes to 0 just because the potential is, forbids from visiting the origin in some sense. Is this clear? Okay? So let me just make a summary of this. If I have a function with a given L, this should start like that. Okay? Clear to everybody? Let me erase this. Okay, and let me erase this. Okay. Don't forget this cancellation because it will be re-emerging in less than half an hour, okay? So keep an eye on it. Now, the other case, rho very large. Now, when rho is very large, let's see. Well, this is certainly going to 0 quite fast. In fact, faster than this, okay? So you can certainly get rid of it. Now, this is a constant, and this goes to 0, right? They multiply the same u, but this at least is a constant. This is, on the contrary, going to 0. So this is also not very important compared to this, all right? They both decrease to 0. So in that limit, how would you approximately write this equation? You would say, okay, in that limit, I should require that the second derivative of u, okay, should approximately be equal to a constant, this negative constant, times u. Okay? Is it clear to everybody? This is the approximate form of the equation when rho is very large. And this is negative. This is important. Okay? It's the bound state energy. Now, you have seen this equation before, right? This is the usual free particle equation. Laplacian second derivative equal to a constant. However, it's not a positive constant, it's a negative constant. So there are no oscillatory solutions here, but there are the usual solutions that decay. So the solution of this are, in fact, e to the plus or minus some lambda times rho. What is lambda? How is lambda related to E tilde? Well, simple. Take the second derivative. The second derivative is minus 1/2 lambda square, okay, when you take the second derivative, times the same function, and this should exactly equate E tilde. Okay? Clear to everybody? So the way this function behaves for very large rho, it's commanded by the energy, which we don't know yet, okay? So the important thing is that they are related hand to hand, okay? Whatever the function does is signaled by the energy. And I have to find the right energy, okay? Remember, only some energies will satisfy our problem in the end, okay? The discrete bound state, okay? So it's important that you understand that for very large rho, I should expect this. And obviously, this should be discarded. The exploding solution is not good. So I want to have e to the minus lambda, where lambda, okay, is related to the energy as the positive square root of minus twice the energy. Okay? Is this clear? Good. Now, suppose I ask you, okay, so you know how this thing should start, and you know how this thing should eventually end up. So just to draw something, okay? For instance, the simplest function, suppose that L was 0, okay? Let us do L equals 0. So the simplest function that has both behaviors, what would it be? A function that starts like rho, and ends exponentially, like this, okay? I'm drawing u here. So a function like a rho e to the minus lambda rho, okay? Like that. This is certainly the good behavior for small r, large r, for L equals 0, obviously, okay? Shall we try to plug this into the equation and see if perhaps this is a solution, okay? This is a kind of warming up exercise. When you try to solve complicated equations, it's a good idea to do particular cases and get the feeling of what the things are going to be, okay? Never start from a very complicated equation without dissecting it into smaller things, okay? The nice thing about L equals 0 is that, for instance, this term is not there. So it's a simpler equation, okay? Let's try. Okay. Should I want to write this thing here. So lambda KL is always square root of minus 2e, okay? And I also know that, well, whatever. Okay, so let us see. If u is equal to constant rho e to the minus lambda rho, let us calculate the first derivative. The u in d rho is equal to a. There are two terms. Take the derivative of this and you get e to the minus lambda rho, or leave that untouched and you get down the minus lambda, right? E to the minus lambda rho, okay? Obviously you can collect the exponential and write this as 1 plus or minus lambda rho, okay? Now I have to take the second derivative because that is what appears in the equation. So I have again a. Let us take the derivative of this, for instance. This will, well, take the derivative of this first. The derivative of that would give you a term minus lambda, right? Times e to the minus lambda rho. And the derivative of this would give you minus lambda, e to the minus lambda rho, but this time you have to multiply by that, okay? Nothing really complicated. Okay, by the way, you can actually combine. You see that this term and this term are really the same. So this object can be written as a. Then there is a lambda square rho e to the minus lambda rho. Well, in fact, e to the minus lambda rho is everywhere, okay? So there is a lambda square rho from here, and then there is a minus 2 lambda without rho, e to the minus lambda rho. Do you agree? Okay. Now, let's plug into there. So I have minus 1/2 that term. So a times lambda square rho minus twice lambda e to the minus lambda rho, the second derivative. Then I have plus. This term is not there. I'm doing L equals 0. So I have simply minus 1 over rho. The function is a rho e to the minus lambda rho. And this rho cancels with that. And then I have here e tilde KL times a rho e to the minus lambda rho. Okay? So let's see. First of all, a drops, which is reasonable. A is a normalization constant. Okay? You will never determine a normalization constant from that. You will determine it from the total integral being 1. Okay? So you never worry about coefficients. Now, let us see. This term here, for instance, is linear in rho as this. Okay? So in order for this equation to be valid, they should be the same. When are they the same? Well, you see, when minus 1/2 lambda square, okay, is exactly equal to the energy, right? Which is, again, this condition, okay? So you see, once again, reinforce the thing that lambda is not arbitrary, is tied to the energy. Okay, so this, we give it. And then what else? Well, let us see. This term, okay, is, let us write the two extra terms. This is plus lambda times e to the minus lambda rho, and this is minus just 1, the same thing. So all this, which is these two terms, okay, should also be 0, because the other two are pairing into a nice 0, okay? So how is this 0? Well, this should be 0, okay? So immediately find from this other requirement that not only the lambda is related to the energy like that, but lambda should be 1, okay? Or, if you want, the energy should be minus 1/2, okay? So this is a solution. If you take lambda equal to 1, and the corresponding energy will be minus 1/2, okay? Minus 1/2. Minus 1/2 what? Hartree, obviously, okay? And lambda equal to 1. So we have indeed found, by just playing a little bit without too many hypergeometrics, we have found a solution, which is indeed the ground state, the famous 1s level of hydrogen, okay? All right, now that we have kind of understood a few things, like the fact that there are exponentials set by the energy, the fact that you should start with some power depending on L, we are ready to tackle the more complicated game of solving the full equation, okay? So I will erase this, or, well, no, I erase this. Okay, so what do? Well, I do the following. I say UKL should be e to the minus lambda, where I know that lambda is related to the energy, the usual relationship, times some function. And, well, let me, for a second, write this function as W. I know, by the way, that W should start like, so I also know that WKL of rho should start like rho to the L plus 1 times some coefficient. Obviously, there are other terms, C1 rho plus C2 rho square, plus like that, okay? So these two things I know. And when you know something, you better extract it, okay, and see what happens for the rest. So I suggest let us change variable, change function, really, and rather than working with an equation for u, let us set up an equation for w, okay? So the point is to calculate, for instance, the first derivative, and the first derivative is equal to the first derivative of w times e to the minus lambda rho. And then there is a term that is minus lambda coming from the derivative of that, w e to the minus lambda rho. Okay? Then I do the second derivative of u. Okay? and I get the following. I get a second derivative of W, for sure. Okay? Then I get what? Derivative of this, which will give me minus lambda derivative of rho e to the minus lambda rho. Okay? Then let's take the second term. When I take the derivative of W, I get exactly a term like that again. So there is a factor 2 here. And finally, I can take the derivative of that, and I get this time a lambda square plus minus lambda square W e to the minus lambda rho. Is this clear to everybody? It's very simple. Okay. So let us plug this expression into here. I have minus 1/2, several terms. 1, 2, 3 terms. Okay? So I have the second derivative. Let me write the derivatives as like that. Okay? So this is the second derivative times, well, you see, e to the minus lambda rho is everywhere. So let me plug it out here. E to the minus lambda rho. Second derivative, then there is minus 2 lambda, the first derivative, and then there is plus the minus lambda square W. So you see the second derivative when transformed into W, it's in fact more complicated. It has second, first, and no derivatives. But that's okay. Plus this, well, this is simply L plus 1 divided by 2 rho square minus 1 over rho times W times e to the minus lambda rho. Okay? I'm omitting all the KL, okay, because, I mean, they are everywhere. All this should be equal to E tilde times W e to the minus lambda rho. And now you see, e to the minus lambda rho is common factor of everything. Okay? So, in some sense, has played this role. The role was in participating in the derivatives, obviously. Also, now, look at this other thing. Since lambda, by a precise idea behind the thing, should be related to the energy, we have commented it already, you see immediately that this term here, which is minus 1/2 lambda square, exactly cancels that. You see? Okay? So this was the whole idea of using the exponential there, because you know that there will be a term in the equation that will cancel out exactly. Okay? Zach with Zach. Okay? You might say, yes, but you have generated other things. No problem. This is better than just not doing it. Okay? All right. So let us rewrite the equation. Okay? And if you allow me, let me just get rid of this. I now rewrite the equation for the function W. So the prefactor of the exponential. This will look like minus 1/2 the second derivative. Then I have minus 2 lambda the first derivative coming from here. Then I have plus L plus 1 over 2 rho square minus 1 over rho, the W. And all this should be 0. Okay, so this is the new form of our equation for W. Okay. Now, if you are confident with this, let us move forward. Now I have essentially exploited my knowledge about large rho. I have still not exploited my knowledge about this function starting like this and then possibly having certain coefficients, which we want to determine. In some sense, our problem is now to determine C0, C1, C2 in such a way that this infinite power series, or in any case, this power expansion, we will comment about the infinite nature in a second. This power series will satisfy exactly this. Okay, let's see. Let me write this in a better way, more compact. This is a sum over Q, where Q is an index going from 0 to infinity of what? CQ times rho to the Q from here, but I have an extra plus L plus 1 prefactor. Okay? Is this clear to everybody? Yes? Yes. Okay? So I have coefficients that I want to determine in such a way that this power expansion, when plugged into this, is perfectly satisfied. Okay, let's see. I have to calculate derivatives. For instance, the first derivative that appears there has what? Sum over Q from 0 to infinity, CQ. When I take a first derivative, I have Q plus L plus 1, and I get Q plus L plus 1 minus 1, 1 power less, okay, in the derivative. And therefore, I have that. The second derivative is as simple as the previous one. It is just CQ, Q plus L plus 1, another power Q plus L, and another decrease of the exponent, minus 1. Okay? Is it clear? Good. Now I have these two expressions. I use them there. Okay? So a bit of patience. Never get too confused by the fact that we have many things. Just write carefully on your paper when you have to practically do something like this. Okay, so I do it explicitly. Every term minus 1/2. The second derivative is there. Sum over Q from 0 to infinity, CQ, Q plus L plus 1 times Q plus L, rho to the power Q plus L minus 1. Okay? The first. Then I have minus and minus is a plus, 2 and 2 go, so I have plus lambda, the first derivative, which is this. Sum over Q from 0 to infinity. I have CQ. I have Q plus L plus 1. And I have rho Q plus L. Okay? This is this term. And then I have these two guys here, plus, let's see. The first is L plus 1 divided by 2. I have this expression where I now have sum over Q from 0 to infinity, CQ, rho to the Q plus L plus 1 divided by rho square. Okay? How can you do this? Very simple. Just write minus 1. Okay? So you see, the 1 over rho square does exactly what the second derivative does. We have already seen this. Remember when we found the alpha which was matching things? Q plus L minus 1 as in that term. Then I have minus the final Coulomb piece, sum over Q from 0 to infinity of CQ, rho Q plus L plus 1 divided by rho, which means no plus 1. Okay? All this should be 0, identically. Okay? So these are now sum of several powers of rho, all matching exactly 0. Means power by power, all the coefficients should just balance to make a 0. Okay? That's a standard trick. Have a differential equation. You really don't know what is the solution. You try a power series after having extracted all the obvious things like an exponential, because otherwise, I mean, you would mix your power series with a trivial power series that has to expand your exponential, which makes the thing much, much less clean. Okay? So that's the idea behind. If you know that there is an exponential, don't blindly put power series, because otherwise the power series has to cope also with the exponential, which, however, has a very simple expression in some sense. Okay? So extract whatever you know and do the power series of the rest. Okay? And that's what we are doing. Okay, so if you are happy with this, so to speak, let us manipulate the things a little bit. We are almost done. Don't worry. It's a bit boring, I realize, but not particularly complicated. You must admit that. Okay, so for instance, let's see. One thing that you notice is that this object here is not written in this here. They're not written in the same way as this. They miss a -1. You see here and here. The second thing that you notice that here there is a term coming from this multiplying this, which is L plus 1 times a -1/2. And here L plus 1 over 2, again, without the minus. And the rest is the same. You see, CQ rho to the Q plus L minus 1. CQ rho to the L Q plus L minus 1. Okay? So you realize that they cancel exactly. Okay? So this piece times that cancels with this. Hopefully, I will not confuse you too much. Now, we are finding again something that we knew already. That the most, the L squared term cancels some piece of the Laplacian, of the second derivative, okay? And this was all embodied in this Q starting to L plus 1, okay? We, in fact, did, as a first guess, that the function should start like that in order for exactly this cancellation to occur. So it's not bizarre. I mean, we made it by just putting this L plus 1 there, okay? Now, if you use this this cancellation, you can, for instance, get rid of this, first of all, which is, I mean, very good. Less things on the board. And you can also simplify this, because here there are several terms, but one is just dropping out. So what remains is, for instance, you can rewrite it as Q times Q plus 2L plus 1. Let's verify it. Why? I have Q times Q plus L, right, from here. Q times Q plus L. Then I have L plus 1 times Q plus L plus 1 times Q. And the extra term is L times L plus 1, which is the one that drops. Okay? So these are the two surviving terms, but if you put things in common, you see that here you have Q times, okay, just put the Q as a prefactor, you have Q plus L plus 1, which is this. Okay? Good. So let me simplify this coefficient in view of the cancellation with the other thing into a Q plus 2L plus 1. Okay? Clear to everybody? So there is no more, okay, let me write this closer. So minus sum over Q from 0 to infinity, CQ rho Q plus L equal to 0. Okay? Bear with me for a few more minutes, please. Don't detach your attention. There's another small trick. When you see power laws like this, which don't match the thing, there is a way of making them match. Relabeling things, okay? So for instance, in this case, you can call this object, call it Q prime plus L minus 1. How should you make Q prime related to Q? It's very simple. Q prime minus 1 is simply equal to Q. Okay? So q prime is equal to q plus 1. Okay? Let us rewrite things in terms of q prime rather than q. So wherever I see q, I should put q prime minus 1. So here, for instance, q prime minus 1. Q plus 1, by the way, is just q prime. And here I have q prime minus 1. And here I have q prime minus 1. And here I have q prime minus 1. And what about this? If q starts from 0, q prime starts from 1. So q prime starts from 1. I've done nothing, just relabeling the things in a way that now makes this more similar to this. Well, the only difference is the prime. But the prime is an irrelevant, I mean, it's up to you to just call it q prime. In fact, I suggest the following thing. First of all, notice that when q is equal to 0, this term just vanishes because of this q prefactor, okay? So this term, in fact, starts from 1 as well. All start from 1. And here, there is just a prime that I can get rid of. I mean, it was just, I introduced to make the change of variable clearer, but there is, strictly speaking, no need for, it's a dummy name, okay? So I can just relabel it Q. Now, you see immediately what is the solution. Everything has sum over the same indices, same powers, okay? So you can read immediately the fact that minus 1/2 CQ times Q plus 2L plus 1 should exactly match, so this thing plus lambda minus 1 sorry, no, I'm being too fast, plus lambda Q plus L coming from here, minus 1 multiplying CQ minus 1, all this should be 0, okay? In order for the coefficient of this generic term Q plus L minus 1 to be 0. You just read it, okay? Now, let me reinstall the indices. Remember that this lambda really depends on some unknown object, some label, which we want to find soon, and from L as well, okay? And now you see immediately that this gives you CQ in terms of the previous. So it's an iterative solution, which is essentially what you want when you write a power series. You want to find any coefficient in terms of the previous one, because after all, C0 doesn't matter, okay? I mean, you can take this as a prefactor in front and say that this is 1 plus C1 over C0 plus C2 over C0, okay? So what you really, and this is a normalization concept, what you really want is this with respect to if you want, ratios are important, okay? Ratios of coefficients. So from this object, you immediately find that CK, CQ, okay, just bring on the other side, is equal to twice this, okay, times lambda KL times Q plus L minus 1. The minus 1 is due to the Coulomb potential, divided by Q times Q plus 2L plus 1 times Q minus 1. Okay? So if I give you C0, okay, you put here Q equal to 1, and you calculate C1. Then you plug it into here, you put Q equal to 2, and you calculate C2. Then you plug it into here, and so on. And you calculate C3, C4, and so on. Everything. Explicitly. You see, here I have just some integers. L, q's that are these integers that I have used as labels, lambda. I can do it for any. One thing that should worry you is that I can do it, in fact, for any lambda, okay? And for any lambda means for any energy, for any negative energy, I can solve this thing. And this should leave you a little bit uncomfortable. Why? Because there is no sign of any quantization here. Any lambda, meaning any energy, is allowed, apparently. And I solved the equation. Right, right. There is a subtle thing here. If this series is really a series, and not a polynomial, and not a finite number of terms, it's tricking you, really. It's giving to you a diverging exponential without, being explicit. Let me make this clear. Suppose that this series really was going on forever, okay? So all the q's. Sooner or later, for very, very, very large q, let's calculate CQ over CQ minus 1, the ratio of two consecutive terms, okay? You know that this is one of the standard criteria to know the radius of convergence of a series, by the way. Calculate the ratio of the coefficients. Now let's see. You immediately read from there. This will be 2 lambda KL Q plus L minus 1 divided by Q. Let me write it as Q squared plus Q 2L plus 1. Okay? Now, for very, very large Q, how would this behave? Q becomes the most important thing. L is fixed, okay? So, and the minus 1 is also not important. So this is roughly 2 lambda KL times Q divided by Q squared is the most important term, Q squared. So this is just 2 lambda divided by Q. Okay? Now, it doesn't take long to notice that this is not very nice. If the ratio of two consecutive things approaches for very large Q, 2 lambda over Q, let's see if we can guess what really the power series is doing. Let me look at this object. Consider this, okay? This function. Let's expand it. If you expand this, you find just a standard expansion from 0 to infinity. You have what? You have 2 lambda times power rho to the power, power q, divided by q factorial, right? This is the expansion. So this is the CQ. Okay, let us calculate CQ over CQ minus 1. So this would be 2 lambda to the power q divided by q factorial divided by 2 lambda to 1 power less q minus 1 factorial. But you see that now this essentially erases everything, but leaves a single factor 2 lambda. And the factorials also are quite nicely behaving. We'll just give you a 1 over q. Okay? So the ratio of two consecutive coefficients in this object is just 2 lambda over q. What we find there. Okay? So this is suggesting that if really the power series goes on forever, then it ends up really into something that looks like e to the 2 lambda rho. Now, why should I expect that, in fact? Because, after all, remember that there were 2 solutions for our problem, one e to the plus and e to the minus lambda rho. We said the one with the plus, forget it, okay? We want the one with the minus. But now, I have the one with the minus. Remember that this is u, okay? And this is only w. So if I take a w which goes like e to the 2 lambda rho, and I multiply by e to the minus lambda rho, what do I get? I get that this thing behaves like e to the plus lambda rho. Okay? So in some sense, the exponential prefactor that we put is not enough to make this very, very crazy guy from giving you the other exponentially exploding solution. Okay? Message, when the power series is infinite, it's really going towards the exploding solution. Okay? So you should not make the power series to be infinite. This power series should stop and should be a polynomial. Is this argument clear? Okay? Let's see how it stops. It's not difficult to see how the power series should stop. There should be an integer in this recursive process. Remember, C0 gives me C1. Then I put C1, I get C2. Then I put C2, and I get C3. There should be some integer. Let's call it K. Okay? K integer, obviously greater or equal to 1. Because C0 is certainly different from 0. Okay? If you put C0 equal to 0, everything obviously will be 0. You don't want to have a wave function that is 0. So C0 is different from 0. But there should be some integer such that Ck eventually is just 0. This integer could be even k equal 1. C1 could be 0, okay? Or C2 or C3, okay? Important is that this thing stops, okay? So how should I, what are the conditions on, for instance, lambda, okay? Now this, by the way, this integer here is exactly what I have used since the beginning as a strange label, which I wasn't specifying, for the possible solutions of this equation. Okay, now, how is it possible that this is exactly equal to 0 when q is equal to k? Well, nothing could be simpler. This object here should be 0. Okay? So for q equal to k, I must have that lambda times k plus L minus 1 is equal to 0. If this happens, then Ck is equal to 0, while Ck minus 1 is different from 0. Okay? So there are only k terms in the power series. But now, what solution is this? Well, this implies that lambda should be 1 over k plus L. Sum of two integers, where L is the angular momentum, could be 0, 1, 2, 3, whatever. And K is this integer that stops the power series, okay? Is the number of terms in the power series. So the sum of two integers is obviously an integer. And this is usually called n. Okay? So n is the sum of the orbital quantum number plus a quantum number that is called radial quantum number. Radial because it determines the number of zeros that the radial function has. Remember, this is the degree of the polynomial for the radial function. The number of terms is the degree of the polynomial. And the polynomial of a certain degree has a certain number of zeros, which are given by the degree. Okay? So in some sense, it gives you the number of nodes of the radial wave function. L, on the contrary, is related to angular things. But the energy doesn't depend on separately K or L, but rather on the sum. Why I say the energy? Because you know that lambda is tied to the energy. So my energy should be equal to minus 1/2 the square of this. Okay? So 1 over n squared. This is the famous series of levels, okay, starting from n equal 1, which is what we already found. Remember our simple solution, okay? Energy minus 1/2. Then I have n equal 2, energy minus 1/2 times 1/4, n equal 3, okay, and so on. Infinite, in fact, okay? So this n integer could be just 1, 2, 3, 4, an infinite series. Now, you should be worried. This doesn't mean that there is one level per value of the energy. In fact, you realize that there must be more than one. Just to tell you something, for every L, there are 2 L plus 1 possible M's. Okay? These are all different functions, but they have exactly the same energy. So there is a degeneracy of this problem associated to the angular part. But there is also, and this is quite standard, atoms in absence of magnetic field always have degeneracy with respect to Lz. In other words, the quantum number of the z component of the angular momentum, m, does not enter the Hamiltonian. Okay? Only L square enters through the Laplacian. Okay? So this degeneracy related to angular momentum is always there in absence of magnetic field. On the contrary, here I have an extra degeneracy. You see that it doesn't matter what is K and what is L. It matters only the sum. Okay? So let us do the exercise of seeing explicitly the possible levels. Is this clear before I proceed? Okay? Now I do explicitly the possible cases. Let me draw better this thing. Okay, so this is now the energy divided by the R3. Okay? So this is the 0. This is minus 1/2. Okay? Okay, I have n equal 1 as the only possible way of getting this thing. And by the way, if you want to have, let me write it just downstairs here. K should be from 1 to whatever, and L should stay from 0, 1, 2. Okay? So the smallest possible value of the sum is 1. Okay? N equal 1. There. And you can do it in one way only. K equal 1 and L equal 0. Let's see. Next. N equal to 2, which means that you have here something that is a factor 4 smaller. So if this is something like this, minus 1 over 8. Okay? In Hartree. Now, n equal 2 can be made in two possible ways. So I should first allow for two possibilities. One is K equal to 2 and L equal to 0. And another is K equal 1 and L equal 1. You see, they have the same energy, but they are different functions. For instance, this function, you see, has L equals 0 spherical harmonics. I discussed, and we will see more, that these are functions that are really not depending on the angles. They are called S waves. Okay? They are totally symmetric with theta and phi, just a constant. Okay? So this is called the 1S level. The S is just tied to the angular momentum. There are letters used for angular momentum. There are S, P, D, and so on. Okay? So, and 1 is for the n equal 1. This object, therefore, accordingly, is called 2S. Now, you see this state with K equal 1, L equal 1. First of all, it has a different angular momentum, L equal 1. It is called P states. Okay? So these are called P states. Still, they have the same energy, so they're called 2p states. Okay? So again, n is the same, it's 2, but the angular momentum is different. And not only that, these have L equal 1. Therefore, it's not only 1, there are 3 of them. Okay? One has m equal to plus 1, one has m equal to 0, and one has m equal to minus 1. Okay? So there are 3 rather than 1 p states and 1 s state. So you see this level of energy is really 4 times degenerate rather than non-degenerate like that. Okay? And if you go on, you will discover that the degeneracy increases. Okay? Because it corresponds to the number of ways you can make an integer, a given integer, for instance 3, out of the sum of 2. For instance, 3 can be made in 3 possible ways. You can either have k equal to 3 and L equals 0 here, okay? Or you have k equal to 2 and L equal 1, or k equal 1 and L equal 2, okay? So 3 possible ways. And each one of these is really more than one level. For instance, the p states are again 3, and the d states that have L equal 2 are really 5. Okay, so these are L equal 2, the so-called 3D states. These are the 3p states, and this is the 3s. All degenerate. You see the degeneracy increases. Now, this is only because we are doing hydrogen. If you do another central potential, the classification in terms of L would still be possible, obviously, but you would discover that, for instance, the 2s and the 2p are not necessarily degenerate. They are split a little bit, okay? So it is just because of the hydrogen 1 over r strict nature that there is this accidental degeneracy of p and s, or p and s and d, okay? For a general atom, the theory is more complicated. There are more electrons. You have to do some mean field type of thing. But the message is that the effective potential that governs the problem is not a pure 1 over r, and therefore you should not expect this perfect degeneracy. Generally, 2s, 2p, 3s, 3p, 3d, they are all close but split. Okay. Next, what about the radial wave function? Okay, the angular part we will study next. They are due to this L equal 1, 2. They have some shapes. Okay, we will study. But the K determines the radial part. Okay. I encourage you to get into this, okay, with some degree of detail, so that you familiarize a little bit with this radial functions that are in the end polynomials, okay? Polynomials of degree k. And the coefficients of those polynomials are just given by this formula for any lambda, okay? So for any energy level, you can plug the corresponding lambda there and calculate explicitly the coefficients of the polynomial, okay? For instance, let us do the simple case here. If I put L equals 0 and K equal 1 and lambda, as you see here, lambda is equal to 1, you immediately see that you must have already that C1 is 0. In fact, C1 would be twice lambda, but lambda is equal to 1, times 1 plus 0 minus 1 divided by something times C0. And you see that this is lambda minus 1, so you have C1 equal to 0, okay? Which is what you expect, because this is a solution with K equal 1, okay? Means no first order term, only C0 is there, which means that W is equal to C0 rho L plus 1, so rho 1, okay? Rho to the power 1, which means that U is equal to C0 rho times e to the minus lambda rho, where lambda is in fact equal to 1, which is, oh, I erased it, the solution we found as a warm-up exercise, okay? So this is the 1s wave function, this one. If you want to plot it, I suggest you to plot the r. R is u divided by rho, okay? Remember, then r is just c0 e to the minus rho, okay? So the 1s orbital, if you plot it, it's like this. It starts from some constant and then is a decaying exponential, sorry, with e to the minus 1 rho, okay? The 1 is because of the precise energy it has, okay? Remember, the coefficients are energy related. That's it. That's the simple exponential that has the ground state of this. Okay, let's do quickly more complicated exercise. For instance, let us do this thing here. Now here, lambda for the 2s, 2p, lambda is equal to 1 over n, so 1 over 2. Lambda is 1/2. Now, let me put here, okay. So, I have, let's see. If I have L equal 1, for instance, suppose that I have L equal 1, then I write, for instance, C1 would be equal to twice. Lambda is equal to 1/2. Then I have 1 plus 1 minus 1 divided by something, just calculate here, times C0. But you see immediately that 1/2 times 1 plus 1 is just 1 minus 1, so this is 0, which is okay. I mean, after all, this is a k equal 1 solution that I'm looking at, okay? And you see that, once again, there is only one term. So the k equal 1 solution, the p state, is one term, again, like here. There's a difference, however, because now I have here L equal 1. So this starts like that. Okay, so it means that this chart starts like rho square. And the other difference is that lambda is 1/2. Okay, so if I divide it by rho, I find this. Okay, so the p state, let's draw it. It starts from 0 linearly, and then eventually goes like a decaying exponential, but with a larger tail. You see that there is a smaller coefficient, so the tail is actually a bit larger than, I'm not drawing it very nicely, okay? But you should realize that this tail is slightly lower than this because of the factor 1/2. Okay, so this is the 1s and this is the 2p. Is this clear? Now, let us do the last thing. Let us do L equals 0, okay? And I have to do, therefore, let me write it again. Lambda is the same, but now this is 0, okay? So I have, for C1, I have this. Now I have to write this. So this is 1 times 1 plus 0 plus 1. So this is equal to twice. This is 1/2 minus 1, so it's minus 1/2. Check if I do some mistakes, okay? Divided by, this is 2. So this is minus 1/2 C0. Okay, so C1 is minus 1/2 C0. And C2, should I calculate it? No, because this is k equal 2. Obviously, I should expect, and I find C2 equals 0. Okay? So for that function, let's write it. I expect W to be C0 times. Okay, so it starts from L equals 0, so it starts with L plus 1, so with rho. Then I have this plus C1 over C0 rho. And that's it. It stops at k equal 1. Good. C1 over C0 is minus 1/2. Minus 1/2. Okay? So now I have rho times 1 minus 1/2 rho here. Therefore, here I have u equal to C0 rho 1 minus 1/2 rho e to the minus same power. Lambda is the same. The energy is the same. Okay? And rho, r, sorry, you divide by this, so C0, 1 minus 1/2 rho e to the minus rho over 2. Okay? So I have a function that eventually has the same thing, but now you see now you see it starts from, for instance, from a certain value, and then when rho is equal to 2, it has a 0. You see, for rho equal 2, and then it becomes negative, and then it does exactly, essentially what this other does, but from the negative side. Okay? So this is the 2s solution. The 2s solution has a 0 for finite rho. On the contrary, the 1s has no 0. The p has a 0 just in the origin due to the angular momentum, essentially, but no zeros everywhere else. Okay? Here there is a 0 in the middle. Obviously, this has to be orthogonal to the 1s. They are orthogonal functions. Remember, they are associated. So in order for a function which is positive to be orthogonal to this other function, this other should have positive and negative things. So you expect zeros. But could not be a 0 in the origin, so it must be somewhere. Okay, this is the 2s. You can go on and do, for instance, n equal 3. I encourage you to do it. So do n equal 3, okay, this states here, and try to plot the 3s, the 3p, and the 3d. And you will see the number of zeros increasing depending on the polynomial in front. By the way, this polynomial are called, they have a name, are called Legendre polynomial. And what we have done is nothing but writing the hypergeometric series, but we have done it with our hands, okay? No books, no nothing. Which is always good to know in some sense. If you have no reference for getting the solution, the name of a certain equation and the name of certain solutions, this is something that saves you, okay? Having no books and no Google would otherwise be catastrophic. Okay? So I encourage you to do these exercises included in the notes. And I encourage you also to exploit similar tricks to solve other problems. For instance, if instead of having the potential minus 1 over rho, you had the potential harmonic potential. Okay? So your V of rho was, well, before you, something like this. Okay? K is not now the integer, it's the spring constant. Or if you want, let's write it m omega squared. Okay? Now, you can play much of the game we have played. By the way, the energies obviously should be now positive, not negative. They are all bound states. In some sense, we already know this. This is the three-dimensional harmonic oscillator, which we know how to solve. It's the sum of three one-dimensional Cartesian harmonic oscillators. We know that the wave functions are product of one-dimensional wave function, we could construct everything, the spectrum and everything. Now, this is one way, but I encourage you to do it in spherical coordinate. I know you have done this with Thomson, so please go back. Go back and try to do it with your hands now, okay? So what is the idea? Getting rid of all the m omega, as usual oscillator length and so on. Next, inquire on how the wave function, call it u, the same thing happens. I mean, you can define a function u for which the equation will look like minus 1/2 the second derivative of u plus L plus 1 over 2 rho square. Rather than having minus 1 over rho, here I expect plus 1/2 rho square, something like this. Okay, check the constants. I might have, okay, equal to EU, something like this, okay? Now, for small rho, you again have an argument similar to the one we have done. It should start with some power that cancels this, because this is the bad guy, okay? So similar arguments will tell you that u starts like rho to the L plus 1. But now the argument for large rho is different. Before, you see, there was a 1 over rho, so something that was dropping here and here, and the thing was constant against the Laplacian. Now, this is there, is in fact big, okay? So how should I take the wave function for very large distances? Huh? You cannot neglect this term, okay? But, in fact, I can require, okay, I can require that this and the Laplacian match together, okay? And if you try to impose that this and this go, you will find that you should have some Gaussian type of tail, okay? Determine the coefficient. I guess it's 1/2, but please determine what is the coefficient of the Gaussian that you are expecting. Notice that this time doesn't depend on the energy, the coefficient here. As we verified in the one-dimensional harmonic oscillator, all the e to the minus x square over 2 were there, and the different energies were just a polynomial in front. Okay, the tail was all the same. This is so you have now this behavior. So if you try to write a wave function, you should say u should go like rho to the L plus 1 times things times e to the minus rho square over 2. Okay, so call this w, repeat all the things, okay, and try to determine the new recursive formulas. Okay, obviously you will learn simple things because you know that the spectrum is just the interplay of 3 harmonic oscillator spectra, and the degeneracy are therefore very simple to calculate from the Cartesian solution, but it's instructive to rephrase everything in spherical coordinates. Okay, there are other exercises that I encourage you to do. One exercise to just get a bit more handy with three-dimensional problems with central potential, you might do, for instance, the 3D free particle, okay, which means no potential. The one that we have already solved long ago, saying that the solutions are e to the ikr with e equal to h bar k square over twice the mass, okay? These are all extended states. But in principle, you might say, okay, let me write an equation now in radial coordinates, and let's try to do the same thing as we did So the Laplacian written as we have done. No potential, okay? In principle, you can still proceed with that thing, okay? It looks more complicated. It is more complicated in some sense. But you will see that what will emerge is essentially an expansion of this plane wave into spherical coordinates, which involves spherical harmonics and Bessel functions, okay? So the Bessel function emerge from tackling this problem in spherical coordinates in a quite natural way, okay? Another problem that you can do is, if you want, the 3D square well. In other words, now the potential is the following. The potential is, so if this is the radial coordinate, okay, it's infinite here, and the particle should stay here, but this is, I mean, you understand. It's like in space having a central part where the potential is 0, and then a surrounding region, we'll call it the radius of the sphere, and outside there is infinite potential. So the particle cannot go outside, okay? So it's like a confinement, but rather than in a Cartesian region like a cube, in a sphere. There will be levels in this sphere, will be quantized, but the quantization condition now has to do with Bessel function going to 0 at the border of this point, okay? So slightly more complicated, but the only way to do it is to use, obviously, radial coordinates, because the potential itself, okay, is specified easily in radial coordinates. If you try to describe this thing in Cartesian coordinates, you would never get out of it. Okay? Questions? Okay. So the plan for next lecture is to discuss a bit more angular momentum. I mean, until now I have kind of given it to you when making appeal to your previous knowledge, if you want. But we will re-insist now on angular momentum and prove all you need to know about eigenfunctions of angular momentum and spherical harmonics. Okay, so questions? Can you repeat the question?
Is there a method, or can we solve this hydrogen problem just like we did for the harmonic oscillators?
The question is if there is an algebraic method to solve the hydrogen problem. I mean, after all, the harmonic oscillator problem was commutators and simple things. And here I have a differential equation, which was quite more boring, perhaps. Now, I think, but it's a recollection of a vague thing, that there are ways of tackling this problem that explicitly use the fact that there is another operator that commutes with the Hamiltonian. That is not just the angular momentum, which is obvious. It is there for any central potential. It is called the Lenz vector, okay, which is also known in classical physics. Now, I believe, if I remember well, that by exploiting that, you can construct more algebraic approaches to this problem, okay? But it's a very far away recollection, so don't take it for granted. In any case, there is more to the structure of the hydrogen problem. There is another operator that is commuting and is responsible for this degeneracy that is not due to central nature of the potential. And I think that by exploiting that, you can do, you can go on more algebraically, but don't ask me now how, okay? In any case, sooner or later, there are problems that are not solved in elegant, few lines algebraic methods. This is one temptation that you should just put into your... Forget that physics is simple algebraic and geometric things. There are concepts in physics that are related to symmetries and elegant and things. But there is also dirty everyday life in which you have confront yourself with some equation, some differential equation, perhaps Schrödinger, which is not solved in an elegant, even not elegant way. It just must be solved on a computer, for instance, which is in some sense the extreme opposite of elegance, okay? The elegance of the algebraic solution and the brute solution on a computer. Both are there in physics, and you should tolerate both, okay?